Here I'm going to go through the answers to the tricky KC questions that I set you today. So question 1, as you can see, I've already highlighted the key information in the question. So now I'm going to have a go at answering part A. What is the equilibrium concentration of iodine? So first thing I'm going to do is write out my reaction equation and just pop under it the information I've got. So I've got the concentration of hydrogen at equilibrium and the concentration of hydrogen iodide. And I'm trying to find this one. Okay, KC expression, nice and straightforward. And I know from the question that KC is equal to 54.1. So I'm just going to write it out again with the numbers in. Okay. I can rearrange this to then work out concentration of iodine, and that will be 3.53 times KC. Just to explain how I work that out, I multiply up this side of my equation and then divide back down, leaving behind my iodine, just in case you wondered. Okay. Popping that into my calculator, nice and straightforward. Answer of 4.7986, 10 to the minus 4. And then just looking back at the question to work out number of sig figs to use. So they've used 3 significant figures in the data, so I use 3 sig fig in my answer. So 4.80 times 10 to the minus 4. I then need to look at my units, and if we look there, my top and my bottom cancel out, so there's no units for this one. Okay. So that's part A done. Part B, what effect would doubling the concentration of hydrogen have on the equilibrium position? So if I double the concentration of hydrogen, my equilibrium is going to shift to the right to reduce that concentration. So my equilibrium is going to shift right. But we know that the only thing that's going to affect the value of Kc is temperature. So Kc, no change. I'm shifting my screen around. What effect would increasing the temperature have? So looking at our delta H value there, our delta H value is bigger than 0, so we know our forward reaction is endothermic. So increasing the temperature is going to shift equilibrium again to the right in the endothermic direction to cool the system back down. And so that will increase the concentration of product, which will also increase my value of Kc. And if you're not sure how I got to that, go back and review the work we did previously on temperature affecting value of Kc. Right, let's go through question 2. This one is slightly harder. So let's just highlight the key information. So we've got Kc for our reaction. We've got 1 mole of nitrogen, 1 mole of oxygen, and that's at the start because it says are allowed to reach equilibrium, so that's the start concentration, and we want to work out the mass of NO. Okay, so first things first, let's write out our table like we've done before. Start, equilibrium, oh, change, hold on. Even I can't remember how to do it today. Right, there we go. So at the start we've got 1 mole nitrogen, 1 mole of oxygen, we'll have no moles of nitrogen. Change will be minus x for each of these, and you need to just take note here of the stoichiometry. So this will be plus 2x. Okay, so at equilibrium we're going to have 1 minus x moles of each of our reactants and 2 minus x moles of our product. These should be in concentration, so we have to divide each of them by V for the volume of our container. But we're not given that in the question, so we're going to ignore that in a minute. So let's just write out our Kc. So Kc is equal to products over reactants in our values here. Kc 0.0036. So 2x over V 1 minus x over V 1 x over V. Okay, that's all our values popped in there. First thing we can do is we can start to simplify this equation. First thing I'm going to do is I'm just going to ignore all the V's. They're all divided by the same volume, so that means that in this case concentration and moles, they're going to be in equal ratios to each other, so we can ignore V. Also, if we look at our bottom here, we could also write this as 1 minus x squared. So we could write this equation as 2x squared over 1 minus x squared. Now I need to have a look at my top row. This is also the same as 2x times 2x, which is equal to 4x squared when it comes out of the brackets. Okay, so our equation now is 4x squared over 1 minus x squared is equal to 0.0036. And change colour pen again. I like doing it in a rainbow. Next thing I can do is I can square root both sides. Okay. So square root 0.0036 gives me 0.06. Then I'm going to square root this one, and you need to square root both terms. So I need to square root the 4 and I need to square root x squared. Okay, so I end up with 2x. And then I also want to square root my bottom term, so I get 1 minus x on the bottom here. Okay. You can ignore the brackets as well if we want to, but I'm going to leave them in just for a minute. Right, then I can start to rearrange. It's like your basic algebraic equation. You want to get your x's on one side and your numbers on the other. So first thing I'm going to do, I'm going to multiply that up to the other side. So I get 0.06 x equals 2x. Multiply out my brackets. Equals 2x. Okay, then I can, again, I want to get my x term, so this term onto this side by plussing it. Seems like a very long-winded thing, I know, but here we go. So I can plus it onto this side, and then I can divide to get my numbers back over here. So x is equal to, or 0.0291 is equal to x. Right, so we've worked out x. But that's not what the question was. The question is what mass of nitrogen oxide was produced. Okay, so we've worked out x. Let's just go back up to our question for a second, for our start here. So our equilibrium moles of nitrogen oxide is 2x. Okay, so remembering that, let's calculate it down here. So here we want mass of NO. So equilibrium moles is 2x, which is equal to our answer 0.0291 multiplied by 2, 0.0582. Okay, mass is moles times mR, so 0.0582 times our mR, which is 16 plus 14, so 30. So our answer is 1.746. Let's make it to 3 sig fig, 1.75 units grams. Done. Woo, that was long-winded. Hopefully that helps. Any questions, please let me know.